My name is Kyle Froh, and today I'm going to be sharing with you some of the research that I've conducted on controlling Lakeshore Technical College's stormwater runoff. Throughout my time at LTC, I've had the chance of actually getting to know Jim Kettler at the Lakeshore Natural Research Partnership. He has informed us that through studies that he has taken with his colleagues, that Lakeshore Technical College actually contributes to the phosphorus that enters Centerville Creek, which is located on campus. Centerville Creek actually runs down to Lake Michigan. And one of the issues that they're dealing with down there is cladophora, an algae that forms due to large amounts of phosphorus entering the creek and the lake bed. What ends up happening is this cladophora washes ashore. It's visually repulsive and it smells terrible. And it actually creates an eyesore for the community around it. It also harbors bacteria, which actually make the water bad for pedestrians to actually swim in as well. And based on this information, I wanted to do something about it. And one of the main ways that phosphorus actually enters our waterways is through stormwater runoff, because phosphorus actually binds to soil particles. And when you have erosion and you have large amounts of water flowing at large amounts of rates that are too much for the grass to handle, you actually fill your waterways with phosphorus, which has then led down to Lake Michigan. Now, one of the things that I want to cover is why we're having this stormwater runoff and why it's entering Centerville Creek. One of the main reasons for this is the fact that we have an urbanized area on Lakeshore Technical College campus. Our stormwater runoff occurs from our rooftops because we're making an impervious surface. It's coming from our sidewalks and our driveways and our roads. And for that reason, it collects the water, it speeds it up, and then it sends it down to the creek at forces that are too hard for the creek and actually degrade the actual creek itself and also adds phosphorus to it. Now, one of the ways that I want to be able to combat this sustainably is with the use of a bioretention basin. My studies and my research led me to this by coming up with one of the most sustainable ways to control the stormwater. What we're used to is all these drain tiles and culverts which funnel the water, speed it up, and cause these erosion problems. Well, I needed to take a step back and look at a way that's sustainably going to control this, and that is through the use of a bioretention basin. Now, a bioretention basin is actually a shallow engineered soil basin that is meant to actually increase infiltration, and it uses plants to filter the water, and it becomes an aesthetically pleasing part of your landscape. Now, bioretention performance comes from the fact that it's actually able to control pollutants. The way it is able to do that is it actually uses the soil to collect those pollutants and instead collect it in the soil and have it broken down by the roots before it travels down to the waterway. Here is information from the EPA stormwater fact sheet, which I took directly from their PDF file online. Now, total phosphorus in their studies was 70% to 83% of total phosphorus was collected inside the basin. And now this is a perfect statistic for me in concluding that a bioretention basin is what we need on campus. We need to control that phosphorus, and this is one way to do it. Not to mention, it collects metals like copper, zinc, and lead, 98% of it. Total suspended solids, 90%, organics, 90%, bacteria, 90%. These are, if you have an impervious surface like a sidewalk, you're not going to see findings like this. This is all going to be down in your creek and instead of in a bioretention basin. Now, part of my research had to lead me to try to find a location on campus that would work for a bioretention basin. Now, the EPA has many standards about where a bioretention basin should go. It should be uphill, and it should also be on slopes that are not over 20%. For that reason, the velocity of water could get too much and actually wipe away the bioretention basin. So you want kind of a larger area with very flat slopes, but still a general downstream to put your bioretention basin in. I actually did some observations on campus in a site inventory analysis class where I actually took a grade shot of the entire area encompassed here on this map This is the location that I decided to choose based on my observations. On the west side of the property, as you can see, here's the agricultural building here, if you're familiar with campus. And over here on the west side is a junkyard. Now, the drainage area this is actually called Drainage Area 2, according to the Abacus Stormwater Master Plan that LTC had done a few years earlier. It actually shows the water flows from this junkyard, which has got heavy metals and whatnot in the water, travels down to this low area here, where it picks up its momentum through culvert C2.4, which was outlined in the Stormwater Master Plan. The water then travels down this narrow channel, past the agricultural building, and down to the T&I, where the T&I has actually been known to flood. Now, based on my grade shots and the work that I did with the trans, I was able to locate an area right about in this location that was kind of a low area with the proper amount of slope to put this bioretention basin. Now you're asking, what is a bioretention basin? You know that it collects water somehow and infiltrates it into the soil, but how does it do it? I created this diagram here to kind of outline the different engineered layers. This depth right here that you're looking at is around 6 feet. And I actually took this information from the Dane County Erosion Control and Stormwater Management Manual, and they took their figures from the EPA fact sheet on bioretention basins. Now, the image here shows a layer on the top of mulch of 3 inches. Now, this is actually sunken down 6 inches on the sides of these mounds. And that point of that is that the water comes down the slope. It's slowed down by these mounds, and then it slowly fills up this 6-inch basin of mulch and plants. The idea of this is so that there's an impervious surface, or permeable surface, so that water can be sucked down initially and not flow over it down to Centerville Creek. So what we do is we put down an engineered soil under this hardwood mulch, and that hardwood mulch is to strictly keep erosion from happening to the soil and whatnot. Now, the engineered soil is actually 33% compost, 33% sand, and 33% sand-loam soil mix. It's all mixed together and creates an permeable layer here that water can go right through. Also, the geotextile fabric is placed in there to keep the engineered soil from the pea gravel. Now, the pea gravel is the beginning layer of the actual retention area. The washstone down here is 12 to 48 inches. Now, washstone has a lot of open space and it's porous, so it can hold a lot of water. For that reason, the water will sit in here before it naturally infiltrates back into the native soil, which is slowing it down and keeping it from running off on the surface. And then the bottom 4 inches is sand mix, and that's strictly to get the water to move because there's a lot of pore space in sand. And then one of the last parts of this is a drain tile. Now this is a fail-safe. If you have water coming into your bioretention basin and it can't control that amount at that time, it'll raise up past that 6 inches and drop down into this drain tile and down into the washstone area and pea gravel area where it can infiltrate in the soil faster. So it can bypass the engineered soil of 3 feet. And then the last part of this is the plants. And the plants are just as important as the system itself. Now, the point of plants in a bioretention basin is there's 3 things: root structure, root depth, and plants use water. Root structure is important because it holds the soil together. If you can hold the soil together, your soil is not going to be washed down into the creek, Centerville Creek for our instance. The next part is root depth. When you have root depth, breaking up the soil and penetrating it way down into the earth's surface, you actually get better permeable surfaces and the water can drain all the way down to the bedrock and to our waterways naturally. And last but not least, these plants use the water. And what better way to use the water than to create beautiful plants and a beautiful landscape and support the native plants of Wisconsin? Which gets me to my next point. You're going to want to use native plants to your region, which in our region would be Wisconsin native plants. The fact is that they can have conditions that get very, very wet. And then 3 weeks later, they can go to drought conditions where it's 90 degrees, it's sunny, and there's no water anywhere to be found. these deep roots allow them to survive those different settings. In a bioretention basin, you're going to get the same exact situation. You're going to have periods of flood, and you're going to have periods of drought. So you're going to need tough plants to be able to handle that, so you're not out there watering this. This is supposed to be a sustainable system. For that reason, you can use native grasses, like I've included here, like little blue stem, big blue stem, Indian grass, northern sea oats, panicum. These species all have very deep roots, and they have great drought tolerance, and they can handle those wet days as well. There's also herbaceous plants. You want to be able to make this beautiful, aesthetically pleasing, but also use the water, which is the intended reason for the bioretention basin. For that reason, you can use Joe Pieweed, prairie blazing star, jewelweed, butterfly weed, boneset. These are all gorgeous flowers in our native prairies that we see driving down the roadways and are just gorgeous, and we can include them in our bioretention basin. Now, there are some maintenance issues that come along with a bioretention basin, just like any other landscape. If you have a turf grass lawn, you're going to have to mow it. You might have to water it. You might have to fertilize it. With a bioretention basin, there's going to be some of those tasks. The first one is that you're going to have to do a yearly or bi-yearly mulch. The mulch degrades, it washes away. It's just something that you're going to have to plan into your maintenance schedule. Also, there's going to be fall trimming of perennials. They're going to have their foliage, brown out, kind of fill out. You can cut that off so that next year they can grow up and be just as gorgeous. And also, these plants can handle salt to a certain extent, but you have to make sure that you pick plants that can handle it. And if you don't, you have to make sure that you don't salt your roadways near a bioretention basin. This can only result in bad plant health and bad soil for the plants. And also, there's going to be collection of debris. You're looking at a low area for this bioretention basin, and not to mention the 6 inches lower from those mounds, where the water is going to be pulling debris and sucking it down into that permeable surface. And for that reason, you're going to have to clean it out, and there is going to be debris along with it. Now, as you can see, LTC is faced with quite a challenge coming up. They have the chance to be a leader in our community and start controlling the stormwater that enters Centerville Creek. It has been shown through studies and tests that we actually contribute to the phosphorus that enters Centerville Creek and down to Lake Michigan. Now, we can do something about it, and something sustainably about it, by using a bioretention basin. A bioretention basin can stop the water, it can infiltrate it, slow it down, and completely eliminate the pollutants before entering Centerville Creek, which is what is supposed to happen in a native setting and not an impervious surface. Lakeshore Technical College has a chance to be sustainable and lead its community to a better future. Thank you very much.